In this lecture, we're going to look at problem solving as it relates to material in Chapter 4. This is a continuation of the concepts onto mechanics. And in this video, we'll look at solubility and precipitation reactions and acid-base reactions. So the first thing we want to look at are the solubility rules. We saw these in our concepts video. Again, we'd like to remind you to print this sheet out. This will come in handy when you're solving precipitation reaction problems, and it will come in handy in your first exam. Soluble ionic compounds, as we saw before, are group 1 and ammonium ions. All the acetates, nitrates, perchlorates, bromide, chloride, and iodide salts except silver, lead, copper, and mercury, and fluorides except lead in group 2. All the sulfates are soluble except calcium, strontium, barium, silver, and lead. And the insoluble compounds start off with hydroxides, carbonates, phosphates, and sulfides, and the exceptions are group 1 and ammonium ion, and for the hydroxides, calcium, strontium, and barium. So we have that in hand. So let's look at some reactions. All right. So how do we approach making a prediction on a chemical reaction? And let's take an example. This is just a prototype example. We have first ionic compound M1X1. The parentheses AQ indicates it's soluble in water. So M1X1 is, for example, sodium iodate. So M1 would be a metal and X1 will be an anion of some sort, either a halide, oxide, or a polyatomic anion. So M1X1 is a soluble salt, and M2X2 is another soluble salt with a different cation and anion pair, M2 and X2. So to discern whether we have a reaction occurring or not, we simply switch the ion partners. So we take M1 to X2 and M2 to X1. And let's consider the first one, M1 to X2. Is that a soluble or insoluble salt? So we answer that question. And then we consider M2X1. Is that a soluble or insoluble salt? And we answer it. So we have two questions, and if either of these gives us an insoluble salt, we have a reaction occurring, and we write the insoluble salt with an S in parentheses next to it. If neither is an insoluble salt, no reaction occurs. So to repeat, if either is an insoluble salt, we get a reaction, and we write down the insoluble salt with S in a parentheses. If neither of the potential ionic compounds is an insoluble salt, no reaction occurs. So now we're going to take these four examples and use the solubility rules and this basic rubric to determine whether we get a reaction, and if we do, what we get as products. Let's take the first one, magnesium acetate plus sodium hydroxide, and we'll look at that one in more detail. So we have magnesium acetate plus sodium hydroxide. Does something happen? Well, we use our approach. We switch the ion partners. Number one is sodium plus the acetate. Is that soluble or insoluble? Well, if you go look at your solubility rules, you'll see all acetates are soluble and all group 1 metal salts are soluble, so that is a soluble ionic compound. The second potential, we switch the other partners and we take magnesium with hydroxide. Is that soluble or insoluble? Well, if we look at our solubility rules, you will see that hydroxides are insoluble, and the exception is group 2. Magnesium's in group 2, but it is a lighter member of group 2. It's one of the higher up members. So that is an insoluble salt. Magnesium hydroxide, like we said in our last video, is in milk of magnesia. Magnesium hydroxide is an insoluble salt. Because of our answer to the second question, magnesium hydroxide is insoluble, we do indeed see a reaction occur. And the net ionic equation is Mg2 plus 2 hydroxides goes to MgOH taken twice, solid. And then the acetate and sodium are spectator ions. We can do the same thing with our next reactions. Here we have ammonium phosphate plus calcium nitrate. Use the same approach as, stop the video, use the same approach as we just did and figure out, do we have a reaction? And if so, what is the product? So if you've gone through and done this yourself, you'll see if we take the ammonium ion with the nitrate ion, so we switch partners there, ammonium nitrate is a soluble salt. That doesn't do anything. The calcium plus the phosphate, of course, that is an insoluble salt because phosphates are insoluble. So that will be our solid product that drives the reaction. And we need to write down all the correct formulas and phases. And so we end up with Ca3PO4 taken twice, solid, plus ammonium nitrate aqueous. And the Ca3PO4 taken twice comes from knowing that calcium has a +2 charge and phosphate has a -3 charge. So we need 3 calciums and 2 phosphates to end up with a net neutral charge for our compound. Next up, we have iron 2 chloride plus potassium sulfate. Stop the video and see if you can solve this problem yourself. Now, considering the possibilities, we have potassium with chlorine, that's potassium chloride, and that's a soluble salt. If we take the iron 2 with the sulfate ion, we see that that is also a soluble salt. So there's no reaction because we have all soluble species. There's no ionic compound that can precipitate out from this solution. Finally, we have lithium carbonate and barium bromide. This is another one to try yourself. Do we see a reaction here or not? So in this case, the lithium bromide is soluble. That doesn't drive a reaction, but barium reacting with carbonate does form a precipitate, so we get barium carbonate solid, and then lithium and bromide are spectator ions. Now let's go on and look at the molecular, total ionic, and net ionic equations. We did these last time with this silver nitrate and sodium chromate example. Let's try a different example. And we'll take the first reaction that we looked at a moment ago, the one we did in detail. Magnesium acetate plus sodium hydroxide gives magnesium hydroxide, and then sodium acetate is our spectator. So we can write this in the molecular form. In the molecular form, we have to write out every chemical species in a combined form. Magnesium acetate is a soluble salt, plus sodium hydroxide is a soluble salt, gives magnesium hydroxide as a precipitate, plus sodium acetate. Now note, we've not balanced the reaction. We could put a 2 in front of the sodium hydroxide and a 2 in front of the sodium acetate, and then it would be balanced. We can break up all of the soluble salts to give us the total ionic equation, which is magnesium plus 2 acetates, and we balance this here with 2 sodiums plus 2 hydroxides, and that will give us the magnesium hydroxide solid, that is the precipitate, with the 2 sodiums and the 2 acetates as spectators. To get the net ionic equation, we simply cancel out ions that are on both sides. And so in this case, that would be the acetate and the sodium. And in order to do that, we end up with magnesium plus 2 hydroxides, because magnesium hydroxide is solid. So that is our net ionic equation. So now you can see all three of these. The lower two are balanced. These are good representatives of what happens. Now on your exam, you will likely get an opportunity to do some precipitation reactions. You should make sure that you're comfortable with the solubility rules and you know how to apply them. So next up, we're going to look at acids and bases. And we know the strong acids and strong bases. If we know those, then if we have another species that's not one of the strong acids or bases, but it is an acid or base, then it's weak. And we know that the reactivity pattern is that acids react with bases, acids don't react with acids, and bases don't react with bases. So opposites attract in this case. So here we can predict products for 3 potential reactions that involve acids and bases. So for the first reaction, we have HNO3, that's nitric acid, plus NaOH, sodium hydroxide. If we mix these two together, we get a salt plus water. And in this case, the soluble salt is sodium nitrate, and we produce water. Water is the driver for this reaction. And you can write a net ionic equation because the nitrates and the sodiums are spectators. So you can just have H plus OH minus goes to H2O as the net ionic equation for this system. For the second one, we have lithium hydroxide plus calcium hydroxide. Those are both bases. Bases do not react with one another. Therefore, we have no reaction. The third reaction is HClO4, that is perchloric acid, reacts with barium hydroxide. We have an acid and a base. In this case, to drive the reaction, we would need 2 perchloric acids for the 1 barium hydroxide to give us water and barium perchlorate, and we would have 2 waters in that case. So the reaction is not balanced there. But we can, in this case, we're simply predicting products. And on your next exam, you'll have an opportunity to do this as well. So you may have some where you're not looking at balanced reactions, you're just saying, do we see a reaction or not? And if so, what do we expect to see for products? Next, we'll look at molarity calculations. This slide came from our previous concepts video. We remind ourselves that we have a solvent, and the solvent is the medium in which the solute is dissolved. And those two combined together make a solution. The concentration of the solution is the amount of solute present in a given quantity of solution. In terms of molarity, that would have the number of moles divided by the number of liters of solution. When you get to Gen Chem 2, you'll see some different concentration units that are moles divided by mass of solvent, which are a little bit different. But in this case, we're just going to work with molarity, moles per liter solution. The basic calculations that we deal with are as follows. The molarity of a solution times its volume will tell us how many moles of solute we have in our solution. And for a solution that we dilute, the concentration is going to go down. So imagine you take some Kool-Aid and you add extra water, the concentration will drop. But the amount of the Kool-Aid solute, that is the sugar and the dye, will stay the same. It will just be spread out over a larger volume of water. So in that case, then the initial molarity times the initial volume equals the final molarity times the final volume. And why is that? Well, molarity times volume gives you moles, And if we're doing a dilution, the moles of solute before is equal to the moles of solute after. You simply added solvent. And the variables are defined here. Mi and Mf are the initial and final molarities, and Vi and Vf are the initial and final volumes. So Mi Vi equals Mf Vf, that is a very useful equation. You will use it this semester, you will use it in lab, and you will use it next semester, and in any subsequent lab work that you do involving solutions. Let's take an example problem, and this will involve a dilution. A stock solution of potassium iodide has a molarity of 0.2500 molar. What volume of this stock solution is needed to make 250 mils of a 0.1 molar solution? So if we're going to use it as a stock solution, we're always going to end up with a more dilute solution, and this one goes from 0.25 down to 0.1. So we use our M1 V1 M2 V2 calculation, or Mi Vi equals Mf Vf. We plug in our initial molarity, our unknown volume, our final molarity and final volume. We solve for V, and we see it is 0.100 liter, or 100 milliliters. We put the period on the 100 to indicate that there are 3 significant figures in our answer. The last piece we'll look at are acid-base titrations, which we discussed last time. Titrations are controlled reactions where we take 2 partners that react, for example, an acid and a base. You can also do precipitation titrations. They're just not nearly as common, but they are done for analyzing a variety of species. In particular, chloride, for example, is analyzed using a silver titration to precipitate silver chloride. And so we have a standard solution and an unknown solution, and we have to have some way of discerning when we've reached chemical equivalence, and that's what we call the endpoint. And for acid-base titrations, we used colored indicators that will change color as we go from an acid to a base environment. And when we're right at the end point, then that's when the color transition begins to occur. And our example will be the following. We have an unknown acid solution. We titrate it with a standard solution of sodium hydroxide. And the standard sodium hydroxide solution has a concentration of 0.1270 molar. If 50 mils of the unknown solution are put into an Erlenmeyer flask and titrated through a burette with the standardized base solution, and the endpoint is observed at 12.35 mils, what is the concentration of acid in the unknown solution? In this case, likely we could use a phenolphthalein indicator. There are a variety of indicators that will easily detect the endpoint for this titration. So we take our Mi Vi equals Mf Vf, or M1 V1 equals M2 V2 calculation, because we know at equivalence the number of moles of acid will equal the number of moles of base. So the molarity of our unknown times 50 mils of that unknown acid is equal to the 0.127 molar of the standardized base times the volume needed to reach equivalence. And as we solve this, we get our unknown concentration. Those are our basic calculations for precipitation and acid-base. In our next video, we'll go on to redox processes.